Okay. Before we jump into the part of the course that we're waiting for, all about computing eigenvalues, um, I need to make you aware that there will not be class on Thursday because there's a SciAm student chapter event that runs from 4:30 to 5:30 that I'll be participating in, a career panel that's aimed at, well, all students to learn about a variety of mathematical careers, whether academic or not. That's held in, oh my God, I don't even know what room it's in. International Center, 101. Okay, which I assume is a big room. So, okay. So, so you don't have better to do during class time, then come and join us. So, it's just 1 hour from 4:30 to 5:30. So, and that's where I'll be. Okay, now I have far too many notes here to get through in one class, but I'll try to just pick out the most interesting parts. Now, in terms of what's in the notes, we have chapter 7, which is on the unsymmetric, so for most general eigenvalue problem, and then chapter 8 is on the symmetric eigenvalue problem. For the most part, I'll be dealing with the unsymmetric one, and then I'll occasionally specialize, because the symmetric eigenvalue problem really is much simpler. Things are just so much nicer. So I'll kind of be going back and forth between the two chapters. Okay. Now, we talked a little bit about eigenvalues before. Whoops, I forgot to push these things back like I usually do. With terrible noise. Quickly go through those definitions again. So we have AX equals lambda x. X is the eigenvector, non-zero. A is n by n. We'll generally assume that A is real. Lambda is the eigenvalue. And that could be complex even if A is real. But if A is real and the eigenvalue is complex, then what that means is the eigenvector is going to be complex too. But there's one other similar relationship that we'll need a little bit, and that is if I basically take the Hermitian transpose of everything, so I have y Hermitian transpose A is equal to lambda y Hermitian transpose. So y is called a left eigenvector. Okay. There's a lot of jargon that I need to give here. So when I say that lambda is an eigenvalue of A, then I can say this, that lambda is an element of this set that I write as lambda of A. So this is called the spectrum of A. So that is the set of all of A's eigenvalues. Okay. Now, so the reason why I want to introduce that notation now is I could say the following, that just by taking this relationship and transposing it, that if y Hermitian transpose, if the left eigenvector of A, then with eigenvalue lambda, then just plain old Y with no Hermitian transpose is a ordinary eigenvector. In this case, you can also refer to it as a right eigenvector. Of a Hermitian transpose, and the eigenvalue in this case is lambda conjugate. Okay, well, actually, I guess I didn't need that notation after all. I was going to use it to describe more concisely what's going on, realized I couldn't. Because this notation here, lambda of A, is used to describe only eigenvalues for right eigenvectors. So strangely, we don't even say like left eigenvalues or right eigenvalues. Okay. We won't be using left eigenvectors very much, but I want to make you aware of them. Now, what I've also showed you before is if AX is equal to lambda x, and x, I want to reiterate, is non-zero, therefore A minus lambda identity times x is 0 just by rearranging and factoring. Therefore, this matrix A minus lambda identity is singular. Therefore, its determinant must be 0. And this expression, determinant of A minus lambda identity, is called the characteristic polynomial of A, and it has degree n. So it means that we have n roots that are the eigenvalues. But they could be complex, they could be repeated. So only when you take into account any multiplicities can you really end up with n values. But what this also means is if A is a real matrix, then the eigenvalues either they're real or they occur in complex conjugate pairs, just like polynomial roots do. Okay. Now, quick review of other terms that I've brought up before. Rho of A is the spectral radius of A, and that is the maximum absolute value of all eigenvalues of A, or complex modulus if need be. We also have the trace of A, which is defined to be the sum of all the diagonal entries, but that is also the sum of all of the eigenvalues. And finally, the determinant is the product of all of the eigenvalues. And I'm using this notation, I use it from time to time, lambda I of A. So when it's not clear from context which matrix I'm talking about, I'm going to use this referred to the ith eigenvalue of A. Generally, we order the eigenvalues from largest to smallest in absolute value, or complex modulus. So trace is a sum, determinant is a product. And so in the case of a 2 by 2, you can use trace and determinant to uniquely determine the eigenvalues. Okay. Now, the funny thing is, in your first linear algebra class, like 326, where normally one would learn about eigenvalues for the first time, although it seems that no matter who's teaching 326, they never actually get as far as discovering eigenvalues. And maybe it shows up in the other undergrad class, 426. They do, right? Yeah, I should hope so.
We did a lot of this.
Yeah, because otherwise it's pretty sad. What they normally do is you're doing a small matrix, like a 3 by 3 or whatever, and the way you compute eigenvalues is, find the characteristic polynomial, compute its determinant, find its roots by whatever means, see if you can factor it, and chances are if it's a homework problem, probably you can factor it. And that is the exact opposite of how eigenvalues are computed in the real world. And that's what this chapter is going to be all about. Although we won't actually get to a part of computing them until next Tuesday, but some important properties will be covered to set all that up. Okay, so first new term that we have. A subspace, and I'll call W, in, actually, need to make it complex, so Cn. Is called an invariant subspace of A if the following is true, that if you have a vector x that is in the subspace, then A times x is also in the subspace. So multiplying by A keeps it in the subspace. A one-dimensional invariant subspace would be just an eigenvector, because you have an eigenvector, you multiply it by A, it's just multiplied by the eigenvalue, it's still in that one-dimensional space. So you can think of an invariant subspace as a generalization of eigenvectors to higher dimensional spaces. So an interesting relationship that comes about is, let's suppose we have an invariant subspace, and it's dimension k. And let's suppose that I have some matrix X, where X is n by k, and it ranges W. And what that means is, the only way that can happen is the columns of X are a basis for W. So let's suppose that we have this k-dimensional invariant subspace and we have a basis for it. Okay. Now, what that would mean is, if I multiply those basis vectors, those columns of X, by A, well, because it's a invariant subspace, each of the columns of AX are also in this subspace W. So that means that AX, well, if I pick out a column, xj, so I'm going to assume, like I usually do, column partitions. X is x1, x2, up to xk. So if I just pick out a column multiplied by A, then it would have to be a linear combination of these same vectors. So I have some constants. Okay. Yeah, so something like that. So there's some constants Bij that I use to linearly combine the columns of capital X to describe this vector. Because this vector is in W, any vector in W can be described in this way. So what that means is, I can say that AX is the same as XB. So by taking all of these vector equations and putting them together into one equation, then I get this relationship right here. Okay. Now, but the thing is, this matrix is A is n by n, X is n by k, X is n by k, B is only k by k. All right. Okay. So this is what the kind of relationship that we always have whenever we have an invariant subspace. That multiplying A by X gives you some linear combination of the columns of X. Okay. Now, here's why this is interesting. Let's suppose that I have an eigenvalue and eigenvector, not of A, but of B. Okay. Oops, those were wrong notes. Okay. So suppose I have an eigenvalue eigenvector pair of B. So By is equal to lambda y. Well, now what I'm going to do is multiply both sides by x. So I have x by is equal to lambda by. Lambda is just a constant, so I can move it around wherever I need to. But xb is ax. Whoops. That should be an x on the right side, not a b. Okay. So now I can group these together. And so if I call this z, x, y is equal to z, so az is equal to lambda z. So if lambda is an eigenvalue of b, it's also an eigenvalue of a. In other words, the spectrum of b is a subset of the spectrum of a. My thermostat's acting up again.
Subset or subspace?
Subset.
Okay. Now, let's take this to the extreme. Because I said the invariant subspace W is dimension k, but I never said what k is. Because k could be anything from 1 to n. So now, let's let k be equal to n. So now I have the same relationship. So I have ax equals xb. Now, x, remember, x has linearly independent columns. Its columns form a basis for a subspace. But now the subspace is dimension n. So now, so since the columns of x are now a basis for the entire vector space, and they're linearly dependent, X is a square invertible matrix now. So now I can say that X, I can multiply both sides on the left by X inverse AX is equal to B. Okay. And furthermore, this relationship still holds, except now, instead of just being a subset, the spectrum of B is now equal to the spectrum of A, because both have n elements now. Okay. So when that happens, we say that A and B are said to be similar. Okay. And this relationship between A and B is called a similarity transformation. This is our most important tool for computing eigenvalues and eigenvectors, because we can take our original matrix A that we want the eigenvalues of, multiply it on left and right by matrices that are inverses of each other to get this new matrix B that has the same eigenvalues. And that's important because suppose B is a structure where it's easy to get the eigenvalues. That's how eigenvalue finding methods proceed. They apply transformation after transformation to A to whittle it down to some eigenvalue revealing form, and there are your eigenvalues. Now, what we'll see is that the best transformations to make are ones that are orthogonal, where the inverse is the transpose, so we don't have to do any work to invert, because we definitely don't want to do that. And the methods you'll see are based on that idea. But there's one problem. What is an eigenvalue revealing form? We don't even know what to aim at. We don't know what our goal is. Well, okay, maybe I brought it up before, so you might remember from then, but it's not part of this current discussion. And besides, I want to prove it. So, there. Okay, so, so for what kind of matrices can we easily find the eigenvalues? Which is also the same thing as for what matrices can we easily compute determinants? Okay, so I'm going to suppose this matrix B that might result from a similarity transformation has this kind of block structure: B11, B12, 0 for the lower left block, and B22. So suppose we're able to find a similarity transformation to get that form, and I'm going to assume that B11 is P by P. This is Q by Q. Therefore, B12 has to be P by Q. And P plus Q would therefore have to equal N. Okay. And let's suppose that Bx is lambda x. So x is an eigenvector of B. And let's break x down into two parts, x1 and x2. So x1 is the first p elements, and x2 are the last q elements. So now what I can do is look at this multiplication, bx equals lambda x, using the block structure. So what I have is b11, b12, 0, b22, x1, x2 is equal to lambda x1, x2. So if I carry out the matrix multiplication, I get b11, x1 plus b12, x2 is equal to lambda x1. And then for the second row, I get 0 times x1, and then b22, x2 is lambda x2. All right. Now, let's look at a couple of cases here. And I wish I had not run out of board space, but okay. Well, I'll just carve out this area here. So there are two possibilities. x2 is not 0, and x2 is 0. Now, let's suppose that x2 is non-zero. We look down here, we have an eigenvalue-eigenvector relationship for B22. So what we can say is that the eigenvalue of B happens to belong to the spectrum of B22. Now, eigenvectors must be non-zero. So let's suppose that if x2 is 0, then we can forget about this relationship and we go up here. And now this term goes away. And now what can we say about the eigenvalue? Well, if this term is gone, then if you look at what's left, what can we say about the eigenvalue now? So similar statement to this.
That B1.
B11, yeah, because now if B11 x1 is lambda x1. Because if x2 is 0, x1 must be non-zero, because the vector as a whole must be non-zero. So, well, that covers everything. So any eigenvalue of B must belong to the spectrum of one of these two diagonal blocks. So that's how we get an eigenvalue revealing form. Get something that is, block upper triangular. Then that breaks the eigenvalue problem down into, so instead of dealing with this n by n matrix, we can look at the eigenvalues of this p by p matrix and this q by q1. In other words, what we have is called, very important term here, decoupling. The eigenvalue problem for B decouples into two smaller problems. Okay. Anyone who's read my KSS papers lately might be familiar with that term for various reasons. Well, depending on which ones you looked at. Okay, because this is one of my favorite things to happen in numerical linear algebra when an eigenvalue problem breaks down like that. Because, wow, it's a cool thing to bring about and drastically simplifies things for you. Okay.
So we can write the same thing for lower triangle.
For lower triangular? Yeah, by transposing everything. Yeah, you would get, so any kind of triangularity brings this about. Okay. So, so we can continue breaking this down into something that is not just, block upper or lower triangular like this, of these 2 by 2 block structure, but any number of blocks. So what that means is the eigenvalues of a triangular matrix are just the diagonal entries. Okay, so I'm going to exploit what I just did to get a useful decomposition for us. We've seen many decompositions for solving AX equals B, but here's the best one to use for computing eigenvalues. Okay. So let's suppose that I have n eigenvalue and eigenvector. So eigenvector x, eigenvalue lambda. And let's also suppose that x is normalized. So it has a 2 norm of 1. And eigenvalue must be non-zero, so we can definitely do that. Okay. Next, let's suppose that P is a householder matrix we saw last week, chosen so that P times X is equal to E1, the first column of identity. And we learned last week how we could create that. Before we had an alpha, but alpha was plus or minus the 2 norm of X, but the 2 norm is 1, so we don't need alpha now. Okay, now I can multiply both sides by P inverse, but what do we know about householder matrices and their inverses? The inverse of a householder matrix is its... Yes, but better than that. Oh, because it's orthogonal, we could say the inverse is transposed.
Aren't they equal?
Yes,
Like the original
because it's also
equal?
symmetric.
Yeah.
Yeah. So if I multiply by both sides by P inverse, like to get X by itself, that's the same as multiplying by P. So I have that relationship. Isn't that freaky? So now what I can do is, if I look at P transpose AP, so this is a similarity transformation, but I only want to look at the first column. Well, PE1 is x. X is an eigenvector. So I get lambda x, and I pull the lambda out to the front. But P transpose x is the same as Px. Px is E1. So, x is an eigenvector of A, but E1 is an eigenvector of P transpose AP. And what that means is, if I look at the whole matrix now, well, we know what the first column is. It's just lambda and then all zeros below it. And then we don't care what the rest of the matrix can be anything. So we have, so the rest of the first row I'll call some vector B transpose, and I'll call the rest of it this n minus 1 by n minus 1 matrix, I'll call that B. So this is a 2 by 2 block structure that I have over there. And the eigenvalue problem has decoupled. So the eigenvalues of A are equal to lambda union the eigenvalues of B. In other words, I've trimmed the eigenvalue problem down for an n by n matrix to an n minus 1 by n minus 1 matrix. I've peeled off one eigenvalue, and now I can focus on B to get the rest of the eigenvalues. So reducing a problem to one slightly smaller in this manner is called deflation. Another very important term about eigenvalues. So you find one eigenvalue, you get it out of the picture so you can focus on the rest. Using a Householder transformation, that is deflation. So now what I can do is I can do the same thing on B. If I can find n eigenvector of an eigenvalue of B, I can make a problem slightly smaller still and just keep going with more Householder transformations. So here's what I get in the end. So by continuing this process, I get what is called the Schur decomposition. Which has this form. A is equal to QT Q Hermitian transpose, where T is upper triangular, and this is similarity transformation because Q is a unitary matrix, so the complex version of an orthogonal matrix. And the eigenvalues of T are the eigenvalues of A. So, in other words, it's also the diagonal of T. So the diagonal entries are the eigenvalues. So this is how algorithms for computing all the eigenvalues of a matrix work. The goal is to compute the Schur decomposition by using orthogonal similarity transformations to reduce A to upper triangular form, so then you can just read the eigenvalues off a diagonal. And so you get the Schur decomposition. The only one unfortunate thing about this, though, and unfortunately I won't have time to cover it during the semester, this gives you the eigenvalues. It does not give you the eigenvectors unless A is symmetric, because in that case T is not just a triangular matrix, it's a diagonal matrix. And then the columns of Q would be the eigenvectors. If it's an unsymmetric matrix, we get the eigenvalues, but there's actually a whole lot more work to do past this point to get the eigenvectors. Now I'll be able to talk a little bit about that, but not cover the full thing. It's a huge pain, by the way. So the symmetric eigenvalue problem is so much easier. Okay. Now, depending on your linear algebra background, you may have heard about matrices being diagonalizable, and I'll say a little bit more about that. Not every matrix can be diagonalized. You can't always use similarity transformations to reduce A to diagonal form, but every matrix does have a Schur decomposition. You always can get that, and so that's why eigenvalue finding methods use a surety composition because you always have it existent at least. Okay. Because really all we can say is the first column of Q. That's an eigenvector, but otherwise we don't know. Okay. Although what can be said, this might help a little bit. If Q is written this way, Q1, Q2, up to Qn, then we can say that the span of the first several columns, any number of columns, as long as you start with the first one and go in order, that is always an invariant subspace of A. Right, so for instance, Q1 is an eigenvector. Q2 is generally not, but you can use Q1 and Q2 together to get an eigenvector. So it's something. Okay. So actually, I can make and actually I'm going to call these are called Schur vectors. So I can make a slightly stronger statement than I did a while ago. I said that these are eigenvectors, A is symmetric. But I can say this, Schur vectors are the same as eigenvectors if A is normal. A normal matrix means that it commutes with its own Hermitian transpose. So if you have that quality, which would certainly be true if A is symmetric, because then you just have A squared on both sides, or if it's skew-symmetric, so A is equal to minus A Hermitian transpose. But other matrices still, any normal matrix, surety composition gives you eigenvalues and eigenvectors. Okay, and what's nice about that is the eigenvectors are orthonormal, a very nice property for them to have. Okay. All right, so but now I want to return to more general matrices because sorry, before I do that, that means that T is a diagonal matrix. So I guess you wouldn't call it T anymore, you could probably call it D. Okay. All right. So in the case of a normal matrix, we can reduce A to diagonal form using a similarity transformation. So if A is not normal, can it be reduced to diagonal form? Meaning, is this possible? P inverse AP equal to a is that ever equal to a diagonal matrix? Okay. So if this is possible, we say A is diagonalizable. Whereas in this case, we could say a little bit more. It is unitarily diagonalizable. And I say unitarily because the matrix Q, QHQ is identity. Now, if it's real, we call it an orthogonal matrix. But when it's complex, we call it a unitary matrix. Make a note of that. Q is unitary. So if there's a unitary matrix that reduces A to diagonal form, it's unitarily diagonalizable. But here we're talking about a general invertible matrix. that might not be orthogonal or unitary at all, that would also reduce A to diagonal form. Okay. Now, one thing we can definitely say is so due to time, I don't, for proofs in the notes, I won't go for the whole proof here. If now we can always say distinct eigenvalues have linearly independent eigenvectors. Okay. So in fact, what I do is I prove in the notes, if I have k distinct eigenvalues and then k corresponding eigenvectors, then you can prove by induction that all the eigenvectors are linearly independent. So what I can say from that is, if A has n distinct eigenvalues, so A lambda xi is equal to lambda I xi. So these are the eigenvalues that are distinct, and the eigenvectors that go with them. Then all of these eigenvectors are linearly independent. So I have, if I can form a matrix X from all of these eigenvectors, then that would be a matrix that has linearly independent columns. Therefore, it is non-singular or invertible. So I can say that AX is equal to XD, where D is a diagonal matrix consisting of all of those eigenvalues on the diagonal. And I can multiply both sides on the left by X inverse and get a diagonal matrix. X inverse AX is equal to D. So in that case, A is diagonalizable. So that's one case that can easily be described. So A may not be a normal matrix, but it can still be diagonalizable. It's when you have eigenvalues that are repeating, where the picture gets a whole lot murkier and numerically challenging. Okay. My pages are all out of order. Okay. Now, I'll see if I can do it more. Okay. Oh, yes. Thank you. That would have pissed me off. Okay. All right. Now, so suppose an eigenvalue repeats, but there's different kinds of repetition that I need to talk about. let's suppose I have an eigenvalue of A. There are two kinds of multiplicity. The algebraic multiplicity of lambda, and I'll call that, I'll call this lambda I, so because we're referring to all the eigenvalues lambda 1 up to lambda n. So I'll call this multiplicity mi. I'm sorry, the algebraic multiplicity. Now what I mean by algebraic multiplicity, that is equal to the number of times this factor, lambda minus lambda I, is a factor in the characteristic polynomial. So in other words, the actual multiplicity of lambda I as the roots of that polynomial. So in other words, lambda minus lambda I to the mi divides the characteristic polynomial, which is the determinant of A minus lambda I. That vertical bar means divides. Okay. Now, the other kind of multiplicity is the geometric multiplicity. And I call that Gi. And that is equal to the number of linearly independent eigenvectors that eigenvalue has. And the way these multiplicities relate is multiplicity must be at least one. Every eigenvalue has at least one eigenvector, but the geometric multiplicity can at most be the algebraic multiplicity. So here's how multiplicities relate. Okay. Now, the interesting case is if the geometric multiplicity is strictly less than algebraic, then we say that the eigenvalue is defective. So in other words, that matrix will not have a full set of linearly independent eigenvectors. So all it takes is to give one defective eigenvalue, A is not diagonalizable. Okay. Another term is if both multiplicities are equal to 1, then we say the eigenvalue is a simple eigenvalue. So it only occurs once as a root of a characteristic polynomial. There's only one linearly independent eigenvector to go with it. Okay. Now, if you're able to figure out all the eigenvalues of your matrix and also figure out their algebraic and geometric multiplicities, this leads to a very interesting decomposition that every matrix has. Very different character from the Schur decomposition. And that's called the Jordan canonical form. I remember learning about this when I took a graduate linear algebra, not numerical linear algebra, just plain linear algebra class as an undergrad. And we spent a lot of time on this, and I did not really understand it back then. At least now I can say I do. Hopefully it can make sense to you guys. The Jordan canonical form is A is x, j, x inverse, where J has this block diagonal structure, J1, J2, up to JP. And these are called Jordan blocks. And here's a structure of each Jordan block. Each Jordan block has some eigenvalue of A all along the diagonal and ones directly above on the super diagonal, unless it's a it's a 1 by 1 block, in which case it's just lambda I by itself. Okay. Now, what do these blocks mean? So first, the number of blocks, which is P, is equal to the number of linearly independent eigenvectors. Of A. So if A was diagonalizable, all you would have is n blocks, and each one would be 1 by 1, having only an eigenvalue in it. Okay. Now, what else I can say? I want to relate this to the two types of multiplicity. Because an eigenvalue can have more than one Jordan block associated with it. So the number of blocks that have a certain eigenvalue, lambda I, on the diagonal is always equal to the geometric multiplicity of that eigenvalue. Because what you see here, this matrix here is not diagonalizable. It is the quintessential non-diagonalizable matrix. It has one eigenvalue, one distinct eigenvalue, lambda I, and it has one eigenvector, which is just E1. And then you'd have to complete a basis, you need what are called generalized eigenvectors, which I won't get into today. All right. And then the algebraic multiplicity of this matrix, one eigenvalue is just the size of the matrix. Okay, so the number of blocks is a geometric multiplicity. The sum of the sizes of these blocks that correspond to this particular eigenvalue, that is equal to the algebraic multiplicity. So if you have the Jordan form, you can basically read off of it the algebraic and geometric multiplicity of each eigenvalue. Wherever these entries occur, like the first column of each Jordan block, the corresponding columns of X are eigenvectors. Okay. So let me give you an example of a Jordan form. That has 3 Jordan blocks. So first we have a 3 by 3 Jordan block with eigenvalue 2. And then we have a 2 by 2 block with eigenvalue 3. And then a 1 by 1 block with eigenvalue 2. So if you look at the two eigenvalues we have, 2 and 3, we look at the, so I'll call this lambda 1, which is the largest, and lambda 2. Actually, I'll just write like that. Okay. Now, if I make a chart here, algebraic and geometric multiplicity. So, based on what I've written here, what is the algebraic multiplicity of the eigenvalue 3? It's 2. What's a geometric? Yeah, because there's one Jordan block, so the number of blocks gives you geometric. The size of a block, because there's only one in this case, 2 by 2. The 2 gives you the algebraic multiplicity. What about the eigenvalue 2? What is the geometric? It's 2, because there are 2 Jordan blocks that go with it, and what's the algebraic? 4, yeah, because you sum up the sizes of those 2 blocks. So this is a very undiagonalizable matrix that this Jordan form goes with, because it's a 6 by 6 matrix, but there are only 3 linearly independent eigenvectors. So, and then so to complete a basis of the whole space, you take those 3 eigenvectors, and then you have 3 generalized eigenvectors. You can complete a basis.
Excuse me. So lambda 2, why is not 3? You count the last one also? Yes.
Okay, yeah, for purposes of determining multiplicity, this is lumped in with this one. Because of a number of blocks to get geometric, and then you add up the sizes of all of them to get the algebraic. Yeah, so if this had been any other value, then that would have algebraic and geometric 1. Okay. Any questions about this one? All right. Now here's a really sad thing about the Jordan canonical form, because let's suppose that this matrix was to change just a little bit. So I want to change this entry here from a 2 to a like 2 plus something. So 2 plus epsilon. Imagine epsilon being as small as you can imagine, like smallest floating point number. Then what happened is that's a distinct eigenvalue. So this is no longer a Jordan form. The Jordan form of this matrix, if I change this 2 to 2 plus epsilon, is that entry would have to become 0. This eigenvalue is distinct from all the rest. So it would have to have its own Jordan block. So the Jordan form of a matrix, once you change an entry a tiny bit, completely changes the structure. And this entry changed only a little bit. The other entries, say we don't change at all, this entry changes from a 1 to a 0. And this is the kiss of death numerically. Because what this says is, the Jordan form is not a continuous function of the entries of whatever matrix you want the Jordan form of. When that happens, if the slightest change in the matrix can cause a change that big from 0 to 1, you can't compute it numerically, because any numerical method you could use to try to compute this, how can you possibly trust a result? If you have 2 eigenvalues that are really, really close together, how do you know that they are really supposed to be distinct eigenvalues? Or maybe they are really the same and there's just some round-off error. How do you treat that? How can you tell which it is? So that's why numerical analysts don't compute the Jordan form. It's one of those commandments. Like, you don't explicitly compute the inverse. You don't try to compute the Jordan form, because you cannot compute it reliably. And that's why we use the Schur decomposition instead. That is a continuous function. Most decompositions are, because you're not relying on some structure like this. So the Jordan form is the only one that really behaves that way. So by working with surety composition, we can more reliably compute the eigenvalues and then try to get the eigenvectors. Okay. Now, actually, this is a nice segue into the next section, which I'll do as much as I can. Let's see, where are my pages? Okay. Dang it. Okay. Wow, this section's bigger than I thought. Okay, well, I'll do what I can these last 12 minutes. Because I want to talk about perturbation theory. If a matrix changes, what can be said about the eigenvalues? How much might they change? Okay.
So perturbation and distinct are the same.
What?
Concepts. Perturbation and distinct are the same.
Well, I mean, perturbation is you're making a change.
Yes, like the small thing like epsilon.
Just adding some epsilon to something. That's what I mean by perturbation. That happens to cause this new distinct eigenvalue to appear. Yeah. Okay. Okay. Now, okay. This one's not really a perturbation result, so I'm not going to touch that one, at least not now. Okay. So one theorem is, I see that, I remember using it a lot when I was a student, it's called the Bauer-Feich theorem. What that says is if A is diagonalizable, okay, those eigenvalues along the diagonal, and if there's some value mu that is an eigenvalue of a perturbed matrix, A plus E, then what we have here is actually a upper bound on the difference between this eigenvalue of the original matrix and eigenvalue of a perturbed matrix. So the minimum, the minimum distance between mu, an eigenvalue of your perturbed matrix, and some eigenvalue of your original matrix is at most the condition number of X, your matrix of eigenvectors of A, times the norm of your perturbation E, where you can use any P norm, like 1 norm, 2 norm, infinity norm, etc. Okay. Now, a way to interpret this is, suppose A is almost non-diagonalizable, which would mean that some of these eigenvectors, if over linearly dependent, might be almost linearly dependent. That means that the condition number of X would be large. So if A is almost undiagonalizable, then a small change in the matrix could still cause a large change in the eigenvalues. So another way to interpret this is if A is close to a normal matrix, which would mean that the condition number would be 1, that would mean that the eigenvalues of a spectrum of A is less sensitive to perturbation. So having eigenvectors that are more linearly dependent, preferably orthogonal, makes your eigenvalues less sensitive to perturbation. That's the key lesson from that. Okay. Now, in fact, eigenvalues have their own condition number, if you will. At least if it is a simple eigenvalue. In other words, multiplicity 1. Okay. Because we can measure sensitivity of a linear system for Ax equals B. That's a condition number. We'd like to have something like that for eigenvalues. Okay. So let's suppose that Ax is equal to lambda x, and we also have a left eigenvector for the same eigenvalue. So lambda has a right eigenvector x and a left eigenvector y. Okay. And this is something that is true in general. Okay. Now, this would come from, this is Jordan form, A is equal to x, j, x inverse. And I can define y to be x inverse Hermitian transpose. So this x is a column of big X. This y is a column of big Y. So what we have is y, Hermitian transpose x, is equal to identity, just from the way it's defined. Therefore, y, Hermitian transpose x of vectors, would be equal to 1. And this just comes from the fact that big X, taking the ith column, is at little x. Big Y, taking same column, is little y. Okay. So we have this normalization that their inner product happens to equal 1. Now, I'm going to look at a perturbation of A and how the eigenvalue changes. So A of epsilon, x of epsilon, is lambda of epsilon, x of epsilon. This is something similar to Ax equals B, in fact, to derive a condition number. And I'll define A of epsilon to be equal to A plus epsilon f. So we're perturbing by some matrix F. It's scaled by epsilon. And for convenience, I'm going to assume that the norm of f is equal to 1. So epsilon is the size of the perturbation. So now what I can do is I can differentiate with respect to epsilon. And what I get is A x of epsilon, or x prime of epsilon, plus derivative of this, which is just going to be f, x of epsilon, and I need to use a product rule on the right side, and I get lambda x prime plus lambda prime x. And then what I could do is plug in epsilon equals 0 everywhere. So ax prime of 0 plus fx is equal to lambda x prime plus of 0 plus lambda prime of 0 x. Okay. Oh, back. Okay, not much further to go. Then what I'm going to do is take the inner product of both sides with my vector y. So y Ricci transpose ax prime plus yfx is equal to lambda yhx prime plus lambda prime yhx, which is 1. Now what I could do is, okay, this is, oh, it's something strange is going on here. Okay, is that fx? Oh, right, duh. Y is the left eigenvector. So that's lambda yh times x part of 0. That term matches this term, so these terms cancel. Right. I was like, where'd all my terms go? Oh yeah, right. Now this gives me, because lambda prime is 0, that's basically the sensitivity of lambda prime, of lambda to perturbations. So absolute value of lambda prime of 0 is equal to this expression, which is less than or equal to 2 norm of y, 2 norm of f, which is 1, times 2 norm of x. Okay. So, but the thing is, the cosine of the angle between x and y is normally defined to be inner products divided by the norms, the 2 norms. But the inner product is 1, because they were normalized that way. So I get 1 over yx, normal y, normal x. So that is 1 over lambda prime. So I can say that lambda prime is less than or equal to the absolute value of secant theta. Okay. So, so this is a secant of the angle between the angle between x and y. So I define this to be the condition number of the eigenvalue lambda. I should mention lambda has to be a simple eigenvalue, multiplicity 1, because if it's not simple, then this doesn't work. Because if it's a repeated eigenvalue, especially if geometric multiplicity greater than 1, I need to be sure to pick out the correct corresponding eigenvalues and left eigenvector and right eigenvector to make this work. So with a simple eigenvalue, I only have one of each. So I have a well-defined condition number. Otherwise, you have like a multi-value condition number. Okay. So the way we interpret this condition number, if I can just find the right page. Frustrating. Here we go. Is an order epsilon perturbation in A leads to an order epsilon times this condition number perturbation in lambda. Okay, so so the thing is, if x, so another way to put it is, if x and y, the left and right eigenvectors, are parallel, that's the ideal situation, where order epsilon change in A causes only an order epsilon change in the eigenvalue. But if the but what can happen is, let's suppose that they're nearly orthogonal. Well, cosine of 90 degrees, pi over 2, is 0. So secant will be going to infinity. So if the eigenvectors, left and right eigenvectors, are nearly orthogonal, then a small change in A could cause an arbitrarily large change in that eigenvalue. So when you have a normal matrix that's unitarily diagonalizable, the left and right eigenvectors are exactly the same. So they're parallel, ideally conditioned. That's one reason why the symmetric eigenvalue problem is so much nicer. You have stable, relatively insensitive eigenvalues. But for a general matrix, not really. So, okay. So that's all I could do for today. Oops, sorry, I ran 5 minutes over. But we'll